The track on the railway works best when trains run smoothly across it. This requires maintenance and eventual renewal. For both renewal and maintenance, there is one piece of kit that engineers put their faith in regularly, and that's a tamper. You may have seen these special trains parked up in a siding or passing through a station. But do you know what they do and when they do it? No? Well, let's find out. Before we dive into tamping, we need to look at the construction of the railway, particularly the ballast. Understanding this will show you why tamping is needed and its importance. Then there is also line and level to look at. Ballasted track construction utilises ballast stone to support the sleepers and ultimately the rails. The ballast has a number of functions in the track system, which I go through in the video shown in the top right corner in detail. For this video, we're going to concentrate on its role in supporting the track, its level of compaction, and its ability to allow the track to be moved. Ballast provides a non-fixed support to the sleepers and rails, transmitting the load from them to the formation and then the ground. This creates what is known as the track support zone. Provided it is in good condition, it does not allow the sleepers to longitudinally or laterally move unless manipulated manually or by machine, and it withstands the forces of passing trains. Ballast stone is chosen for its angularity, which allows the individual stones to lock together, preventing movement and turning a collection of stones into a more coherent and rigid structure. But for this to happen most effectively, the stones must be forced together or compacted. This is also known as consolidation. When consolidated, ballast is at its most solid and able to resist the forces imposed on it, especially lateral forces most seen on curves or from thermal expansion forces. To consolidate fully, ballast needs to be packed tight and then subjected to load to force it together, like that of multiple trains passing over the track. However, the good times don't always last. Given the weather and other factors that ballast and the railway in general are subjected to, its deterioration over time is inevitable. This leads to track geometry faults such as dips in the track or voids under the sleepers. But the nature of the ballasted track construction means that work can be undertaken to lift the track, pack in new ballast and restore the track to good running order. So it is maintainable without major levels of intervention to a certain extent. However, other factors can lead to more severe issues such as wet beds. To finish this section of the video, before we go on to tamping itself, I want to cover line and level. It's important to remember that the track is designed in both horizontal and vertical planes. The horizontal, or line as it is often known, is the left and right turns. When it comes to moving it, moving track left or right is achieved with slew. The vertical, or level, is the gradient that the track goes up or down, as the world isn't flat, as much as track engineers would like it to be. Then there is also the cross level, or cant, which is the difference in height between the two rails. For more on this, check out my video on cant in the top right hand corner now. Both the vertical and the cant are changed with lift, physically picking up the track and packing more ballast underneath. To allow the track to be slewed, it often requires a certain amount of lift to be applied. Think dragging an item across an uneven floor as opposed to lifting it up and then putting it back down. The one thing we won't cover here, because tampers cannot do it, is lowering the track. To lower the track requires the removal of ballast and then reinstating the track at a new height. On to tamping. At its core, there are two parts to the tamping process: the packing of the ballast, then the line and level correction. Let's look at how tamping works, then we'll look at where it's used. When we say tamping, we're normally talking about a train or on-track machine, OTM, that contains a tamping bank. A tamping bank has a number of pairs of tines that penetrate the ballast. A pair of tines are positioned so that they enter either side of the sleeper to force ballast under the sleeper. A pair is then situated either side of the rail. This ensures the track support zone is fully covered. Remember, the track support zone is the area that the force of passing trains is transferred through into the ballast and then the ground. The tines are spade-shaped at the end and vibrate. The vibration, at about 35 Hz, allows the tines to easily penetrate the ballast, while the spade shape allows the tines to effectively move the ballast. Once inserted, the tines are pushed into the area under the sleeper, pushing and packing ballast into the area. To help this happen, a set of clamps grab the railhead and lift, which in turn lifts the sleepers, creating a space for new ballast to be forced into, as well as allowing existing ballast to change its position. Primarily, any voids under the sleeper are filled, improving the support for the sleeper above. When first developed, and for a number of years, this was the sole role of tampers. However, over time and with the evolution of technology, the role has expanded. This brings us on to the second part of the operation, the line and level. A key function and use of modern tampers is to implement or restore a track geometry design. The clamps that lift the rail can lift it to a design position and also move the rail laterally to slew it. This allows both the line and the level to be changed. So now we've covered the process of tamping, let's look at why tamping is undertaken. Tamping operations are undertaken in two main forms. First is design tamping. As the name suggests, a design can be loaded into a tamper and it will then implement it. This involves the survey of the site prior to the works, the creation of a design, and then finally implementing of the design with the tamper on site. This sequence requires multiple accesses to the site, a competent surveying team and designer. However, an exact design can be implemented on the track. This is used on track renewals or where a specific or complex track geometry issue exists. The final position of the track can be tightly controlled or specific issues addressed with a high degree of accuracy. The other method is an automatic method that goes by different names, including maintenance tamping, gecko, or automatic linear correction, ALC. To determine the rail's location, tampers have a recording wheel set in multiple places that the onboard computer can use to map out the track's profile, both vertically and horizontally. In the automatic method, the tamper undertakes a recording run of the site it is working on. The computer then determines the best design or corrections, then works out the lift and slew values required, and then implements it. This method of working does have a number of advantages over design tamping. A survey and design is not required, with this all effectively being undertaken by the tamper on site. For a section of track that has a number of minor track geometry faults, this can be an efficient way of treating them. Given it can undertake design on site, it can also increase the output of the tamper, tamping greater lengths of track. There is also the flexibility to change to a different site at short notice and still undertake work. However, it does have some drawbacks. The train's onboard system may struggle with more complicated geometry layouts. Long geometry issues can also be a problem. If a track bed is in a bad state overall, a maintenance tamp is unlikely to make it perfect. It will just make it less bad. Before we look at the specific reasons that tamping is undertaken, I wanted to take a minute to say that if you're enjoying this video and finding it useful, and you want to know more, do check out my collection of ebooks available at the link below. You can get my free Guide to CAN ebook by simply popping your email in the form at the link below as well. Back to it. So we've covered how tamping works, along with the two types of tamp that can be done, but where is tamping needed? New track installation. Once new track is laid, the final track geometry design needs to be implemented, as well as ensuring all the sleepers are uniformly and consistently packed. Ballast renewal. In some circumstances, only the ballast is being renewed. This can be small sites of wet beds or large sections of poor ballast. After the new ballast is installed, the line and level of the track need to be restored, and the new ballast again packed under the sleepers. Sometimes a tamper is not available, so a tamping bank attached to another machine can be used, or in some cases, handheld vertical tampers. A section of track may be generally poor for track geometry, and a tamper can efficiently improve that compared to manual intervention. There is also cyclic top faults that can stretch over long distances and is a particular risk to freight trains. Both of these situations can lead to speed restrictions being implemented if they're not addressed. Then there is also isolated track geometry issues, such as a twist fault that manual work may have failed to remove or only temporarily solve. A tamper can give a high quality job while also being able to improve the track either side of the fault that may be acting as a trigger point for the actual fault itself. So, while tamping ensures a good packing of the ballast, it does, conversely, reduce consolidation. The movement of the track and the vibration disturbs the track and breaks its consolidated state. This reduces its resistance to lateral movement. Subjecting the ballast to load is the only way to reconsolidate it. However, after tamping, with the track now fully packed and with better line and level, once consolidated, the overall benefit is a massive positive. So, in the immediate aftermath of tamping, mitigations such as speed restrictions or inspections may have to be implemented. This is especially important during times of hot weather and when thermal forces come into play. One solution to this is known as dynamic track stabilization, DTS, which is a vibrating unit that simulates the passage of multiple trains while holding the track in position. This gives a certain amount of consolidation prior to the first train, thus giving the track higher initial lateral resistance. Two more things that require consideration about tamping: ballast quality and component condition. For tamping to work effectively, the ballast has to be of good quality, still retaining its angularity and shape, and be generally free of fines. Poor ballast that is full of grit, fines or soil cannot be moved effectively by a tamper. The tines succeed in making nice holes in the ground and not much more. On sites like this, or where wet beds are present, stone blowers are more effective, but really the ballast needs to be dug out and renewed. Lastly, the overall condition of the components needs to be considered. Given the tamper uses the rail to lift and manipulate the track, the connections between the rail and the sleeper need to be solid. If the screws on wooden sleepers, for example, are not secured to the sleeper and acting more as pegs, when the rail is lifted, the sleeper may simply stay put. This reduces the effectiveness of the tamping considerably, sometimes making it completely pointless. Speaking of track components, have you checked out my Track Component Guide ebook? It's one of the range I have available. Check the link below. I hope this video has given you an understanding of what tamping is, how it can be used, when and why it is done, and the things that need to be considered. Don't forget to drop a comment below and hit that subscribe button. Thank you.